All right. And this one is the demonstration of the examples using SAS. So here, I demonstrate this using the ELABS version or the Citrix version of SAS 9.4. And first of all, I specify a working directory by creating a library called Lecture 7, LEC7, LEC7, and then I specify the directory. So remember, if you use a elapsed version, so you need to first put the client and the $, and then things after this will be the directory on your local computer. Okay. So you can see I create a folder or create a library called Lecture 7. And it was so when you run it, so it will show on the Explorer, and you will have a folder called Lecture 7. So this includes the two data set we're going to use for the examples. So the first one is the systolic blood pressure example. The second one is the tire example for the randomized block design. All right, so it's going to be a little bit slow because I'm using the elapse version, and also I'm recording this at the same time, so we tend to be very slow. All right, so first of all, I want to run the one-way ANOVA using the proc ANOVA. So remember, this is the ANOVA with only one factor, which is the age group. So I want to see if there's a significant effects of age on SPB. Basically, the analysis variance will be through a F-test testing if the mean of systolic blood pressure are simultaneously equal across the age groups. So there are 4 age groups, remember, defined by the age variable in this data set. All right, so here I can run this model by highlighted. Again, it's going to be very slow because I'm recording and using the Citrix version. All right, so here's the output. So here we only have one factor, age, have 4 different levels, 1, 2, 3, 4, and these are the number used by SAS. And the first table is the table for the model with the 3D work freedom. And this is exactly the same ANOVA table we're going to use for the F-test, because there's only one factor variable here, which is the age. So the age will be the same as this testing for the model, because age is the only one for model. And you can see the top one and the bottom one, and this one is for the whole model, and this one is for age. So they're going to be equivalent in terms of sum of square and the mean square and the F score and the p-values. But in the first table, it also gives you the sum of square and the mean square error, because that's the residual part for the one-way ANOVA. So the F value is actually being calculated by using the MS mean square for the model, or the same as mean square for age, divided by the mean square errors, basically 28 91 divided by 69, and we end up with 41.5 F value. And if we use this F value in terms of the F distribution with numerator degree of freedom equal 3, denominator degree of freedom equal to 60, we get a p-value, highly significant p-value less than 0.0001. All right, and then we actually claim age is a significant effect for the mean SPB in terms of there is not a simultaneous equal mean across the 4 age groups. So that's the conclusion for this one-way ANOVA. And you probably note here we use the procedure proc ANOVA, and there's not going to be a type 1 and type 3 sum of square. And also, in this case, type 1, type 3 sum of square will be the same because age is the only one variable there. So here we just call the ANOVA sum of square using the ANOVA procedure, proc ANOVA. Okay. And then the second one is basically we run this ANOVA, but we ask SAS to provide the group means of systolic blood pressure for each 8 groups. So that's to say at the end, SAS will output a table and give the estimate of mean for systolic blood pressure for age group 1, 2, 3, and 4. All right. So we run this procedure. Okay. Basically, the things before this are all the same as the first ANOVA procedure we run. But at the end, you see we have the estimate SPB for age 1, 2, 3, and 4 together with the standard deviation for the mean. So standard deviation for the mean is actually just the standard error. And also we have the number of observations for each age level. All right. And the next one is for the, okay, is the procedure we use here for the Tukey correction or the Tukey-Kramer multiple comparison method for the pairwise comparison after we run the ANOVA. So remember, at ANOVA, we reject the null hypothesis and believes the mean of systolic blood pressure are not simultaneously equal across the 4 age groups. So that means at least one pair of the group comparison will have a significant difference. So here, remember the Tukey test, we do an exhausted pairwise comparison among these 4 groups. So the total number of pairs will be 4 choose 2 equal to 6. So that's to say there's going to be a 6 pairwise comparisons by running this ANOVA procedure with the Tukey Kramer test. And here we also ask for the CL for the difference, which is 95% confidence interval for the difference. And also we set the nominal alpha level as 0.05. All right. Then we run this model. All right, and again, everything before this is the same as the first for the output for the first model we run. And here, at the end, we got this multiple comparison table with alpha level equal to 0.05. And also they have the error degree of freedom equal to 60, which is the 63 minus 3, 3 degree of freedom for age groups. And they also give you the error mean square, which is the same as the mean square error, MSE, and also the critical value of student noise range, so which is value you want to compare with. And in the second table, so this will give you all the pairwise comparisons. So as I said, the unique number of pair is 4 choose 2 equal to 6. So in this table, it's actually include the sum of the redundant information. So for example, the comparison between group 4 and 3 is the same as the comparison between 3 and 4. The only difference is the sign, because you use 4 minus 3 versus 3 minus 4. The only difference is the sign. And the confidence interval will be reversed with a different sign, but however, the significance level is the same. So here we can pick up the unique comparison is 4 versus 3. The other thing is, remember, SAS will automatically treat the largest number of the factor as a reference group. So it's starting with 4 instead of 3. So compare 4 with 3, 4 with 2, 4 with 1. So these three are unique. And also 3 with 2, 3 with 1, and then 2 with 1. So these are the unique ones, but all the others is basically just the redundant information. The only thing difference is the reverse of the sign. All right, and then we see the significance for significant difference between group 3 and 4 systolic blood pressure, and also between group 4 and 2, between group 4 and 1, between group 3 and 1, between group 2 and 1, but not between group 2 and 3. So this is to say the difference in mean systolic blood pressure between group 2 and 3 is only 3.4 at 0.05 test level. It is not statistically significant, so there's no stars for here. So remember, if we have the 3-star, which means a significant result at the 0.05 test level. All right, so this is for the two-key Kramer method for multiple comparison after we run the F-test for one-way ANOVA. And the last one here for one-way ANOVA is we do the contrast. So remember, the contrast is we can compare any functions of the group means. So here we want to compare the mean systolic blood pressure for age group 1 versus the average of the mean across group 2, 3, and 4. So this is equivalent to you put the coefficient C1, C2, C3, C4 equal to 1, negative 1/3, negative 1/3, and negative 1/3. So this will guarantee that all the coefficients sum up to 0. Right, and the estimate is basically we're doing the same test, but here we can use number 3, negative 1, negative 1, basically divided by 3. And here we're basically testing the same thing, but there will be a little bit difference in the output. So we can just first run this procedure. All right, I probably need to rerun it. Sorry about the a little bit slow by using the elapsed version. All right, so here's the output. So here again, the first output are basically the same as we run previously. So at the end, so it gives us that the results for the multiple comparisons. The first one is we're using the contrast statement. And the second one is the one we use the estimate. So here we give the 1 degree of freedom test. So it's basically comparing the mean systolic blood pressure for age group 1 versus the average of mean systolic blood pressure for age 2, 3, and 4. And then the F-test give a p-value less than 0.0001. And this is the F-test. And for using the estimate, it's basically doing the same thing, but it won't give you the sum of squares for that and also the mean square error. So instead, it gives you the estimate. So the estimate here is the estimated difference between the mean systolic blood pressure of age group 1 versus the average of the mean age systolic blood pressure for age 2, 3, and 4. So the negative 17 is the expected difference in the systolic blood pressure, and also give the standard error for that estimate. And here, SAS actually run a t-test instead of f-test, but the t-score is actually the square root, or we can see the f value is the squared of the t-score. And then the f value will be exactly the same because they are too small. So both will give a p less than 0.0001. All right. So these are basically all the test results, the SAS results, SAS code and SAS output for one-way ANOVA. And then for two-way ANOVA, we're primarily using the procedure called PROC-GLM. And the first one is the test we call the full model, because this is a model with both factor A, factor B, and interaction between factor A and B. So here, factor A is the smoking status, and factor B is age. And then we have interaction between age and the smoking status. So the first one is the model with the interaction. So after we run it, so if you still remember, we talk about this output, so the first one is not really the ANOVA table we're going to use because it combined the three effects together. So this is a model combine the smoking's effect, age effect, and also the interaction between smoking and age with a total number of 7 degree of freedoms. So this p-value is actually testing the whole model instead of each separate effects. And we have 3 separate effects in this model. We have smoking effect, we have age effect, and we have the interaction. And the smoking effect, 1 degree of freedom because there are 2 levels for smoking status, and 3 degree of freedom for age because we have 4 age groups, and the degree of freedom for interaction is equal to this one times this one is equal to 3. So 1 times 3. And then this is the type 1 sum of square, and this is a type 3 sum of square, and these are the corresponding F value and the P values for the test. So here, I think the take-home message is we reject the null hypothesis. We fail to reject the null hypothesis. There's no significant interaction. So the things is we can remove these interaction terms from the model, from the final model. And if you still remember, this is the result by using each level comparison with a reference level. So this is the basis for calculating the group-wise or the estimated mean of systolic blood pressure for each combination of the two factors. So based on that model, we can calculate. So for example, non-smoker with age group 1, non-smoker with age group all the way to a smoker for the age group 4. And again, in this table, we have the sample size for each combination of the factors, and also we have mean and standard deviation. So this is basically the standard error for the mean pressure in each subgroup defined by smoking status and age. All right, so remember, we fail to reject null hypothesis, or we say the interaction terms is not significant, so we can rerun this. We run a model without the interaction terms. So this is a model by removing the interactions, and then so these are the code for sorting the smoking status and the age group. And then we have a estimate mean for each group, and then we plot them. So we can run all the way until right here, we can get 2 plots. All right, so we end up with 2 plots. So one is the plotting the systolic blood pressure versus age, but stratified by the smoking status. So the lower one is the smoking status equal to 0, which is non-smokers. The upper one is the smoking status equal to 1, so which is a diamond. And this is for the smokers, and the squared is for non-smokers, and you can see them almost parallel. We do see a very strong effect of age group on the SBB, but there's no interaction because you see there's a parallel of the 2 lines defined by the smoking status. And the other one, the other figure is for SPB versus smoking status. Again, we can ignore the numbers between them. So because we only have data at the smoking equal to 0 and 1. So basically here are the means for the non-smokers of each age group. And here are the mean for smokers for each age group. And the lowest one, the bottom one, is age group 1 with the square. And the second to bottom is the age group 2 with a diamond. And this is age group 3 with a circle. And the top one is age group 4 with a star. And you can basically see there's a strong trend for systolic blood pressure as the age is becomes older and older for the individuals. Their expected value for systolic blood pressure is higher and higher. All right, and then the last one is for the randomized design example using the red data. So here we're basically using the two-way ANOVA, and we use the chemical as treatment effects. So that's the effects we're interested in. And the red is the random block. And then we can use the Y. The Y is the continuous variable for the toxicity level from 0 to 10, and we can treat this as continuous outcome. So because this is, even though it's not a continuous variable, but this is a categorical variable with many numbers. So usually we can treat this as a continuous outcome. And actually, if you check the distribution of this outcome variable, it is not very skewed. It is approximately follow a normal distribution. So that means we can use this as treat this one as a continuous outcome, but they are not really the continuous outcome. So here, if you want to look at the data, so you can double click on that data. So basically, we have the levels by the chemical. So we have three different type of chemicals, 1, 2, and 3. And then the second column is the red, which is a random block, and the Y is our outcome for the degree of toxicity. And then remember, the red is the random block because we randomly assign these chemicals among the reds. And this is a complete random block design because each red will contain both chemical 1, 2, and 3. All right, so therefore, there's going to be 3 times 8 observations, or 24 observations in total, because we have 3 chemicals and 8 rats. So if you go to the bottom, you see the total number of observations is 24. All right, and then we can run. We should close this one first, and then we can run this model. All right, so here's the result. So first one is the test for the entire model. So this including 2 factors, the factor of chemicals and also the factor of the rats. And then we have this error terms. And then we will have a 2 analysis variance table because we use the proc GLM. So the first one is the type 1 sum of square and type 1 F test. The bottom one is the type 3 sum of square and type 3 F test. So well, main interest is to evaluate the effect of chemicals on the toxicity, and therefore we can identify if the different type of chemicals will give a different mean value of toxicity. So basically, this chemical have a 2 degree of freedom because there are 3 different type of chemicals. And then we can calculate the type 3 sum of square, and the mean square is just 25 divided by the degree of freedom 2, 12.5, very easy to calculate. And this happened to give a p-value, F score equal to 7, exactly 7. And then the p-value based on the F distribution was 2 dimension of degree of freedom. So the degree of freedom for numerator is 2, and the degree of freedom for the denominator is 14. And based on that critical value at the 0.05 test level, we got the p-value equal to 0.0078. So this means we at the 0.05 test level reject null hypothesis and believe the mean toxicity level are not equal across the 3 different chemical types. Or in another word, the chemical have a significant effect on the toxicity. All right. So that's everything for the SAS demonstration. And I think you basically can combine the by looking this video together with the previous videos to get a better understanding of the text material or the content. So and that's variance, especially the two-way and no-way is very easy to understand because there's interaction terms. But I can tell the interaction here in no-way is very similar to the interaction in the linear regression. So if you can understand the linear regression, the interaction in the two-way and ANOVA is not very hard to understand. All right. I hope everyone can just look all the videos and get the better. And maybe I think I suggest you to look at these videos multiple times because this is not in-person lecture. So only if you look at this multiple times, you may have a better understanding of these materials. All right. So that's all for lecture number 7.